All right, so let's move on to pressure. So let's just talk a little bit more about the friction factor. I'll give you some information you probably need here. So friction factor, this is the primary consideration for the shear stress part of what we care about here. So if you're going to compute the local friction factor, the local friction factor is sometimes called the Moody, M-O-O-D-Y. So the Moody friction factor. Sometimes you hear the word Darcy. So people will say Darcy friction factor. What they actually mean is the Moody friction factor as represented on the Darcy chart. Okay, so the Darcy is like a diagram. And Moody is the actual name of the friction factor. Okay, anyway, so this is F. This is at a particular location. So F is equal to minus dP dx times 2 times the hydraulic diameter over rho um, that's the mean velocity squared. So if I want to relate somehow the local pressure gradient to the friction factor, this is what I would get. So you also need to like have some chart that goes with this, or a function that you can use to evaluate, which we'll get to in a second. If I want to compute the average, right, so this would be what we call the apparent friction factor. This is like what appears to be the friction factor if you look at a long length of pipe. This is given as F bar is equal to delta P times 2 dH over L rho um squared, where this delta P is the pressure at x equals 0 minus the pressure at x equals L, right, over the full length of whatever the pipe is. So we can get F from a correlation, and then lets us solve for dP dx. And then you also need maybe for the apparent to get like the pressures at the inlet and outlet, or the delta P, and then you could relate that to the average friction factor. Okay, so if I plot these out, let's just do this quickly. Let me plot F, our local friction factor. So this is, let's call this F over here, and this coordinate down here is x. So I'm plotting the local friction factor as a function of position. So what do we expect? Like right at the leading edge, the boundary layer is basically 0. So we have essentially an infinite friction factor. Well, really quickly that goes down. And then at this point here, this dotted line, let's call this x FD H. That's where my flow is fully developed. So what do we expect the friction factor to do? Well, it's going to drop. Just sketch this a little better. It's going to drop. And then as the boundary layers merge, at this point, the friction factor stops changing. It's fully developed. Right? The local friction factor stops changing. So this is now constant. So this is, let's just call this here is F. Okay, so hopefully that makes sense. What about the average friction factor? How does that behave? Well, let me draw it with green here. So the average friction factor, right, we're starting off at an infinite friction factor, and then we're going to like integrate as we go on. So the weighted integral that includes like infinity at 0 is always going to be higher than the current friction factor, right? So you're starting off at infinity, or it's undefined, just like F, and that comes down as well. But you're just integrating everything from wherever you are back to x equals 0. So let's say, okay, we get now to this point where it's fully developed. So now what's going to happen here? Right? Is my average friction factor going to stop changing, or is it going to continue changing? Yeah, so it will continue going down. It will eventually converge or get close, but the average friction factor is always going to be a little bit higher than your local friction factor. So, okay, some things that you can take away from this. If XFD is really small compared to L, we can just use the average, or we can just use the local friction factor in the fully developed region and call that good, right? Because our average here, this one here, is eventually going to converge. So if it's long enough, they're the same thing. It doesn't matter, right? If you're in the developing region, you have a local friction factor that's changing. If you're in the fully developed region, the local friction factor does not change, okay? So all those things are kind of things you want to think about in this. So I want to talk quickly about the thermal considerations for internal flow. We've been talking about just the momentum part of this. So again, let's go through this pretty quickly and stop me if you have questions. All right, so what I want to do here is let's draw the boundary layers and then draw the thermal, the temperature profiles. So here now we're talking about a thermal boundary layer that's meeting in the middle. And I want to sketch out the temperature profile at 3 locations. Let's pick here, and let's pick here. All right, my temperature, let's see, how am I going to map that? So I'm going to draw a temperature as if it's sort of tilted on its side, just like the velocity profile. We're going to draw, if temperature is to the right, it's bigger, and then to the left, it's smaller. You kind of see what I mean. So the temperature profile is, let's say we're holding, at this position, we're holding the temperature at TS. All right, so this is kind of our temperature axis here. So TS, so as we get to the edge of the boundary layer, we're going to run right into T infinity. And then everything in this middle part here is at T infinity. And then again, out here, we're at TS, right? So if you're having a hard time visualizing, just kind of flip this 90 degrees, and you'll see like the temperature kind of does this, right? Where the middle part is at T infinity. So, I mean, that makes sense. We're holding the temperature of the wall at TS, and then the middle part hasn't yet been affected. Now as we get to the fully developed region thermally, that's just saying I'm still out here at TS, same temperature difference, TS and TS, but my profile is kind of established like this, right, where it's basically a parabola. So it's symmetric. The temperatures just meet at the middle. And then once that happens, then nothing changes, right? It's fully developed. So let's see. The velocity is fully developed. The temperature, on the other hand, because we're holding this surface temperature constant, right? So this is maybe an important point. So we're holding the surface temperature constant. So will the temperature profile continue to change or not? I sort of just said it backwards. Will the temperature profile continue to change beyond this or not? I'm holding the surface temperature constant. Right, because you're continuing to add heat, right? Like if you look here, there's a temperature gradient, meaning there's conduction, so there's still heat being added. Where's that heat going to go? It's going into increasing the temperature in the middle. So in the end, you end up with a temperature profile that might, at this point, look something like this. Right? Go far enough down and it's just a straight line. Okay? So this is sort of how the temperatures work out. We can maybe label some things here. So this position here is XFD T. That's the thermal fully developed length. So I think the rest of it sort of makes sense. Like this here is delta T. Right, that's your thermal boundary layer. Some things that you might want to know here. I guess I've put them at the bottom for you. The mean fluid temperature. If I want to compute the mean fluid temperature, how am I going to do that? I would take the integral of the temperature profile, but you have to kind of weight it by the velocity profile. So if I knew the temperature profile and I knew the velocity profile, I could do an area integral divided by the volumetric flow rate, and I would get the average or the mean temperature. So that's how you do that. The convection rate equation here is what this is saying is now I'm trying to compute convection in terms of Ts minus something. Now the important thing that I'm going against is this mean temperature Tm. All right, so the mean temperature is going to be the thing you compute on the left-hand side. So we are not, we're no longer saying Q dot double prime Hx times Ts minus T infinity, right? The inlet temperature. It's the mean temperature at the other end of the boundary layer, right? That's what's important. Okay. Let's see. So that's some thermal considerations. Let's go through the Prandtl number. So this will be real quick, and then we'll get through to the next part. So I just wanted to sketch like what it looks like for the thermal and the momentum boundary layers to grow at different rates. So let's say we have a Prandtl number of greater than 1. So remember, Prandtl number is, let's say, viscous forces over thermal, or viscous dissipation over thermal dissipation. So if I have a Prandtl number greater than 1, that means that the boundary layer related to viscous forces grows a lot faster than the boundary layer related to thermal dissipation. So I would draw it like this, where I'd say, okay, this is, let's say, my delta T. So this is delta T. That's my thermal boundary layer. Well, if the Prandtl number is greater than 1, then the momentum has to grow, the velocity has to grow faster. So it looks something like this. So this here would be delta M. All right, so you can have the boundary layers, excuse me, boundary layers grow at different rates, and you can have different fully developed positions in laminar flow. The opposite is true for Prandtl less than 1, so we could just draw it the same way. So something like this, where now this is delta M, and then here we have this being delta T. So it should make sense. And then the other thing I wanted to show you here was like what happens if you transition to turbulence in terms of the relative rate of boundary layer growth. So let's say we have, let's just sketch out our transition. So you have a laminar boundary layer, and then it becomes turbulent. So that's the momentum boundary layer, delta M. So what happens to the thermal boundary layer? Let's say we have like a Prandtl number such that the thermal boundary layer is growing much more slowly, like this. So what happens in the turbulent region? Like how is the growth of the momentum boundary layer and the thermal boundary layer going to be different or the same in the transition region to turbulence? So think about like what is the mechanism for heat transfer and what is the mechanism for mass transfer in turbulent flow? It's no longer conduction. Yeah, question.
Is all the heat transfer through the viscous sublayer, or all the difference in temperature?
Yeah, so all the difference, like the difference in temperature, the difference in velocity profile is primarily in the viscous sublayer. And the viscous sublayer is a thing that's dominated by momentum considerations, not thermal considerations, right? But once you get past the viscous sublayer, there's this eddy region. So the main mode of heat transfer and mass transfer, or momentum transfer, in the eddy region is the eddies, right? The eddies, the bulk movement of the fluid, right? I can't talk. Bulk movement of the fluid. And that is not dependent on like conductivity of the fluid or viscosity of the fluid. It's just the bulk movement, right? So the same thing is moving momentum and energy in both of those cases. So actually what happens is you get both of them growing together at the same point. Okay? So once you transition to turbulence, that transition occurs based on a momentum consideration, a velocity consideration. Once that transition happens, the thermal boundary layer will grow together at the same point that the momentum boundary layer grows. And then everything beyond that is really dictated by the viscous sublayer, right, out here. The viscous sublayer is not going to change after that transition region, and then you're sort of left with the results of that process. Okay, questions there? Yeah.
So for this last situation, would that mean that X for fully developed for H is equal to X fully developed for T?
Yes. Yes.
Yeah, that was my second question.
Okay. Yep. So what you say is like, okay, XFD, T, or sorry, call it, yeah, T is equal to XFD H, which is also equal to, let's call it X critical. All right, that's the point at which you transition to turbulence. Okay. Okay, one last thing. Let me just sketch. Oh, I already did this, so you don't have to do it. I just sketched out the Nusselt number, so it's very much like the friction factor and the average friction factor. Here we have the local Nusselt number and the average. It's the same considerations. We're integrating past this fully developed point, so average will continue to change. It will eventually converge to the local fully developed value, but it's sort of the same ideas there.